Hello and welcome to this video on combinations of functions. So this is actually pretty much straight from the textbook. This chapter 1.8 is from our textbook. We've been using the same one for at least 10 years. So if there are any remaining questions you have, right, see the textbook. It's a pretty good one. But I'll try to show you guys the simple version of all this. All right, so combinations is kind of like a general word. So we've got like arithmetic things that we can do with functions. We can combine them, adding, subtracting, multiplying, and dividing. That's what I mean by arithmetic. But we also have another way of combining functions that isn't like any of those things, and it's called composition. Composition is a very unique thing that you can only can be done with functions. No other mathematical thing you have ever learned can do this thing that we call composition. This is what, is kind of tricky, but through enough examples you can get used to it. So we're going to learn how to combine arithmetically two different functions, and then we're going to figure out how to compose them through a composition. And then what's not listed here is once we combine them, we'll also be able to find the domain and the range of these combinations. So I don't know why they didn't list that here. These combinations and compositions can also be done and applied to real life situations too. So we will see an example of that in these notes here. So this is the note sheet. There's a homework worksheet that goes with this that should be on my SJ for you guys to start on. And this should have some sample problems that you should see on that homework. So just as two real numbers can be combined by operations of addition, subtraction, multiplication, division, two functions can be combined to create new functions, right? So just like you can combine numbers, you can combine functions. And so these are like the generalized version of these rules. So this over here, everything on the left side of the equal sign, you got to be aware, right? This is like a form of notation. So when it says f plus g, this is kind of just a way of saying f of x plus g of x, right? Like you shouldn't take this literally for what it is. We're not saying f plus g. It's more like f of x plus g of x. But if you ever see it written this way, just know that it means this over here. Same thing with this one, right? F minus g really just means f of x minus g of x. You're subtracting two functions. If you have this, right, this is not, right, let me make this super clear. This is not f times g times x, right? Again, this is a form of notation here. So this is the function f of x times the function g of x. All right, so don't think this. This is bad. No. And then, again, this is not f divided by g. It's really just f of x divided by g of x. All of this is just like a way to like shortcut, So that way you don't have to write all this stuff. You're actually writing fewer symbols over here on the left side. What's kind of special about the division stuff, though, is because of that one rule I told you guys, never divide by 0, we cannot allow this bottom function to ever equal 0, right, because of this rule for a domain. So there's this restriction here. G of x cannot equal 0. And that's going to be important when we talk about domain and range, right? So let's go through some examples, right? So I got two functions here. We're going to take their sum. Right, so remember that was sort of, here's like the shorthand way to write it, f plus g with a little parentheses x here. This is the same thing as f of x plus g of x. And then all you have to do is replace those two things with their actual formulas, right? 2x minus 3 plus x squared minus 1. And all we can do is combine like terms. So the only like terms here are -3 and -1. So my answer is x squared plus 2x minus 4. We can also take the difference, right? That's written as f minus g. And so again, that's going to be, I'm going to go ahead and skip like writing this out. It would be 2x minus 3 in parentheses minus another set of parentheses, put g of x in those parentheses. The parentheses stuff is so important here, guys. You will get the wrong answer if you don't put these parentheses, right? So this would be wrong right here because this negative seems to only be applying to x squared. No, you're subtracting, right? If this is f of x minus g of x, you're subtracting all of g of x, right? Not just part of it. So we got to go back and fix this. All right, so let me get rid of the green stuff. We got to put parentheses around both functions. So now we get 2x minus 3. This minus will distribute, and we'll get minus x squared plus 1. So we end up with negative x squared plus 2x minus 2. Cool. Product, right? That was written in that sort of interesting way, f times g parentheses x, right? That's the same thing as f of x, which we'll put there, times g of x. So 2x minus 3 times the parentheses x squared minus 1. You might be looking at that and thinking, is there a shortcut here? No, there is not. You have to distribute every single multiplication. If I knew a faster way, guys, I would show you, but I don't. So 2x times x squared is 2x cubed. 2x times negative 1 minus 2x. Negative 3 times x squared, that's minus 3x squared. Negative 3 times negative 1 is positive 3. And actually, there's no like terms here that we can combine, so this is actually our answer. Cool. And then quotient, right? So that was f over g of x. So that's going to be the top function f divided by the bottom function g. 2x minus 3 divided by x squared minus 1. Now, we got to go back. This is that special case, right? You have to specify this condition. So for this example, only this last one, I have to say, okay, x squared minus 1 cannot equal 0. Now, that actually has further implications, right? Because we could actually factor this and see exactly what x is not allowed to be. So if I factor it, I get x minus 1, x plus 1 cannot equal 0. And so we can finally say, okay, well, we know exactly two numbers x cannot be. X cannot be equal to 1 or negative 1. So that's actually part of our answer here, right? So this, along with that condition, we have to specify that. All right, so that's something people forget about, is specifying what is not allowed for that quotient example. Then we have composition, right? So this is that really unique thing that we can do only with functions. So it has this interesting way of writing. So you write an open circle for composition, or it means composed with. Remember, every symbol can be like read, almost like reading words on a page. So this is f composed with g of x equals, and then this is sort of like the way we sort of think about it, right? So you kind of want to think, this might be a little far-fetched here, but think like Shrek. Think like an ogre. What do ogres love? Onions. Onions have layers, right? So functions have layers. So essentially, there's like an inner layer here, and then you have this outer layer of f. So the inner layer is the g of x function, and you're taking that inner layer and plugging it into, right? Notice how it's inside of the parentheses for f of x, right? You're plugging another function as the input to another. And they have this little picture here of like how the domains work, right? So you might have an x value in the domain of g. When you plug that into g, all these numbers in your domain get mapped to outputs for the g function. And now we're going to take all these numbers and plug them in to f, and we'll get all of these outputs, right? So we're going to have to be careful about what the domain of this composition is, right? So if we know the domain of g and we know the domain of f and we compose them, we'll be able to say something about, what is the domain of f composed with g. That's a question that we could answer, and it takes some time to think about. Anyway, let's just figure out how to actually do this, right? So f composed with g, right, equals, let's go ahead and just write out what it actually is. So it's this. What I would recommend to you guys is for the first function, I'll do that in green. So f, go ahead and copy the formula for f right here, but then replace the x with parentheses, right? So we'll do, and use a big parentheses actually, right? So like you're going to put a lot of stuff in place of that x. So we'll do big parentheses plus 2. And then this is our inner function. That's going to go in the parentheses, right? So 4 minus x squared. That's all there is to composition. That is literally it. We have basically solved the problem. Our composition is negative x squared plus 6. Just simplify whatever you get once you've plugged in the function, right? So composition will always involve something like this, right? You'll do a set of parentheses, and then you'll put another function in the parentheses. And that's really all you need to worry about. So let's do another one. We can also compose the functions the other way, right? And you might be thinking, well, is it going to be the same, right? Like, I know that 3 times 2 is the same thing as 2 times 3, right? So doesn't that work here? Well, actually, no, it does not, right? So what we say is composition is not, it's an old math property you probably forgot the word for, commutative. Commutative, right? So the commutative property is things like this, right? Multiplication is commutative. You can switch the order and the answer doesn't change. So this is not commutative. So we will, in fact, get a different answer. And you can see this if you just do the problem, right? So this, since the g is listed first, we have g of f of x. And so if I'm following how I did the last problem, now this time I'm going to take the formula for g, and I'm going to replace this with a big set of parentheses squared. Right? You replace the x with a big set of parentheses. But now that g is listed first, the template looks like this. Big parentheses, squared. And then what goes in those parentheses? That's going to be this x plus 2 function, right? This is going to go here, right? Because that's what f of x is. F of x is supposed to go there. So that would be x plus 2. All right, and now we just need to simplify. Of course, you got to work with this. You got to calculate what this is first, and then we can subtract it, right? So like, let's go ahead and do some quick multiplication over here. So you have to distribute all this stuff out. You can't take a shortcut here. You should have a 4x in the middle. So this is going to be what replaces the parentheses on our answer. So we have 4 minus parentheses x squared plus 4x plus 4. And then this minus sign will distribute, right? And we'll get 4 minus x squared minus 4x minus 4. And luckily for us, these 4's cancel. So our final answer is negative x squared minus 4x. And there you go. That's composition. So now, note that in this case, right, if we change the order, we get actually something not the same, right? We could also say, to use that word from that symmetry, like notes in homework, we would say these are not equivalent equations. So, g of f of negative 2. So what happens when I have a number there, right? Originally, we had an x here. So what changes? Well, you actually have a few options, and I'll show you all both. There's actually 2 ways to do this problem. So one way is that you could calculate f of negative 2 just as it is, right? Because remember, this is g of f of negative 2. So this is like the onion approach. So what you do is you start with the inner layer, you calculate this, and then you're going to plug that number into the g function. All right, so we'll calculate that number. Well, I should have kept the square there. F of negative 2 would be, where's the function? Negative 2 plus 2, which equals 0. And so now I want to calculate g of 0. So I go back to the g function. It's 4 minus x squared. So I'm going to have 4 minus 0 squared. And my answer is 4. Cool. That is correct. So that's method 1, the onion method. Method 2, I would say this is like the formula method. Now, this only works if you already have the formula, right? So g of f. So notice we actually already have the formula that we need right there. I don't know why I went all the way around, but essentially we have g of f of x. So if I go from, g of f of x equals negative x squared minus 4x, if all I do is I replace that x with a negative 2, then all I do over here is replace these x's with negative 2, and that's it. So make sure you put parentheses, though, when you plug in numbers, always. All right, so we get negative, this becomes 4, positive 4, and then we get plus 8. And guess what answer we get? 4. Same answer, right? And you should get the same answer. Even though they're slightly different techniques, they should agree with each other. Math is consistent, no matter what angle you look at it. Okay, and here's a nice little real-world problem. The number n of bacteria in a refrigerated food is given by this equation. Okay, it's just a function. We'll deal with it later. And this right here, what is that? That's essentially the domain, my friends, where capital T is temperature in degrees Celsius, and the temperature is given by this equation, where T is time. All right, so we have a capital T for temperature, lowercase t for time. So our temperature is a function of time, and our number of bacteria is a function of the temperature. So hopefully you can see how is this composition thing going to work here. All right, so we'll see in a second. So part A, find the composition. N of t of little t, right? Or we would say N composed with lowercase t. or sorry, capital T, right? So let's do it. Very simple, right? And if you ever forget, just go back to the formula for composition, right? We have it right here, right? This is how you turn something like this into something like this. So let's go down here. So this should be equal to capital N of, parentheses, capital T of, parentheses, lowercase t. Once you have that set up, it should be fairly straightforward. Now in this case, notice how the capital N function has a big T right there and a big T right there. You're going to replace both of those with parentheses. All right, so we get this equals 20 big parentheses squared minus 80 another big parentheses plus 500. Don't forget the plus 500. And then we take our capital T function and that would go in for both of those parentheses right there. 4t minus 2, 4t minus 2. Cool. And yeah, we're going to have to do some quick math here. So you can check me on this. Hopefully I don't make any mistakes. See, I get 16t squared. We're going to get minus 16t and then plus 4. All right, let's go ahead and distribute this minus 80 here. So we get minus 320t plus 160 plus 500. I'm trying to save time in the video by going fast. Multiply, multiply, multiply. Okay, we get 320t squared. Yes. Minus 320t plus 80, then minus 320t plus 160 plus 500. All right, so we end up with 320t squared minus 640t, because this is a like term with this. And then if we add the constants, we get 660 plus 80, that's 740. So this right here is our function. This is essentially n now as a function of little t, right? So notice how the variable changed, right? We used to have big T, right? So I plug in a time now, and it tells me the number of bacteria. So this is kind of more useful, to be honest. B, find the time. So notice how we're finding a lowercase t, time, when the bacteria count reaches 2,000. All right, so really at this point, all we need to do is know where does this 2,000 go now, right? I have this new function, big N of little t equals 320t squared minus 640t plus 740. Where does that 2,000 go? Well, it certainly does not replace these little t's because those represent time. The only place that 2,000 should go is to replace this capital N of t function thing, right? Remember, think of this as like your y value or your output, right? They're telling us the output of the function. They want us to find what is the input that creates this output. All right, so hopefully that makes sense. So we now have an equation, right? 2,000 equals 320t squared minus 640t plus 740, right? And then all we would need to do at this point, I know it seems kind of crazy, 0 equals 320t squared minus 640t. What I'm doing is I'm subtracting by 2,000 on both sides. So this should become minus 1,260. Gross. All right. But we can solve this. Now, since I'm using my iPad and I don't have a TI equivalent here, I'm going to have to do a little split screen action. So this is the function we want. 0 equals 320. I'm going to have to use x instead of t. That's okay. Minus 640x minus 1260. All right, so I'm solving this equation. Whenever you type an equation into Desmos, you just want to look for the x-intercepts. So I can actually highlight this, and there's an x-intercept right there. There's also another one over here, but notice we have a negative number, negative 1.22. That would imply we're going backwards in time, right? So notice, number one, that is not in the domain, right? Negative 1.22, negative 1.22 is not here. So they already told us we're not allowed to do that one. So this must be a false solution, right? This is the only solution that could make sense, and it's a little bit later than the domain they give us, but it's at least more realistic. So 3.222, right? So that either means I made a very small mistake somewhere that I'm not catching here, or maybe the domain should be a little bit bigger than 3. I'm not really sure which one it is, but we're just going to go with that answer of 3.22. And this would be, what is the units here? You always got to have units. Hours, right? Time in hours. Hours. Always got to have units. All right, sounds good. There are a few more examples, which I think at this point I've already taken enough of y'all's time. I might finish these at a separate time and then post these notes in the drive. So that way, if you want to see the answers to these examples, just check the drive for that. But at this point, most of y'all probably got the gist of how to do this. You know, onions, layers, composition. We didn't do as much domain work in the notes here, but that's okay. So the homework will be in my SJ. So just pop it in Notability, work on it that way. It'll be easier to turn in anyway. And thank you for watching.